All right, so in this video, we're going to be looking at several types of rational functions and what their graphs look like. So one type is a graph, a rational function that has no vertical asymptotes. We're going to look at some that have a single vertical asymptote, and then the behavior of graphs that have two vertical asymptotes. So the first case that we're going to look at is the case where there are no vertical asymptotes, and this could happen in a couple of different ways. So any factors that could be equal to 0 may cancel with another factor in the numerator. In that case, we could have a whole. And then any non-canceling factors might have complex solutions and can't be made equal to 0 with a real number. So let's consider our first example, our graph with a whole. So an example like this, we would factor the numerator into x plus 2 and x minus 3. This would cancel the x minus 3, and then the reduced form of the function would be x plus 2. It's nearly equivalent to the original function, except the original function was not defined at x equals 3. And therefore, there is actually a hole in the graph. But if you go to plot this function, even in its original form, most graphing programs will not be able to graph out the point of discontinuity. They will not plot it for you. And so even though your calculator may plot a perfectly straight line, you are still, as a student, going to have to identify the location of that hole. If you put your original function into your calculator and you go to the table and you start plugging in values, you will see that at the point x equals 3, you get an error. And then you can plug that x equals 3 into the reduced version of the function to get the y value of that point. Here, that would be 3, 5, which will be right here. And again, you will have to plot this manually because most calculators won't plot that hole for you. Now, there are other ways to get functions that don't have any vertical asymptotes, and that is having problems where the denominator cannot ever be equal to 0. So if we were to try to solve x squared plus 1 for x, if we set it equal to 0, we would get complex solutions. So this is a relatively simple case. If we have 1 over x squared plus 1, we're going to get a problem like this, where it's never equal to 0. This is always positive. The maximum value of the function is at 1, and then we have a horizontal asymptote on that it approaches on either side. If we have a problem like this, where we have x in the numerator, then there is going to be a place where the graph is going to cross 0 and change sign, but we still have a horizontal asymptote at y equals 0. Now, in a case where we have a single vertical asymptote, our graphs are going to have basically one of two kinds of shapes in terms of the behavior of the asymptote. So near the asymptote, we're going to have behavior that looks like 1 over x, where we approach the asymptote on one side and head to 1 infinity, and then on the other side, we flip over to the other infinity and come back down or back up. If this was a negative, we would flip this graph upside down, but basically it would have the same kind of behavior. It'll go to 1 infinity on one side of the asymptote and the opposite infinity on the other one. If we have x squared, 1 over x squared, then if we have a factor that is repeated, then it could go to the same infinity on both sides. So this one will go to positive infinity on both sides. So let's look at some examples. So here, if we have x over x minus 2, there is an asymptote at x equals 2, and the behavior at that asymptote is that we go to, in this case, negative infinity on the left side, and then we flip over and we come back down from positive infinity on the other side. We do have an intercept at 0, 0, since when x is 0, this whole thing is 0, and you can see that the graph goes through that. We also have a horizontal asymptote at y equals 1, and so that would go through this portion of the graph right here. And again, we would leave the horizontal asymptote and go to infinity. We know it has to be negative infinity. We know it has to be on the bottom side of the graph because it has to go through 0. And then again, it will flip over, change infinities, and come back down in this case, and then reapproach that horizontal asymptote. Now, if we have a factor in the denominator, which is squared, then again, this one is still going to go through 0, but now it's going to go up to positive infinity, and then it's going to come back down from the same infinity. Now, in this case, the denominator has a larger degree than the numerator, and so the horizontal asymptote is going to be 0. But because the graph has to pass through 0, 0, it's actually going to go past it a little bit and then come back up to the asymptote on the other side. Now, if we had a cubic, we would still have a asymptote where we're approaching one infinity, we're staying on that same infinity and then coming back down from it in this case. But because our numerator has a larger degree than the denominator, we would end up with an oblique asymptote, not a horizontal one. And in this last example, we have x squared over x minus 2 squared. So again, the leading term is going to give us a horizontal asymptote of 1. But again, we're going to go through 0 and bounce off the 0 and go back to 1, as opposed to passing through the 0 and heading off to that oblique asymptote. But we're going up to positive infinity and then staying on the positive side and coming back down. So again, if it's repeated an even number of times, we're going to stay on the same side of infinity on the other side of the asymptote. If it's an odd multiple, either by itself or maybe it's a cube, then it's going to flip the sign. If it goes to positive infinity on one side, it'll go to negative infinity on the other, and vice versa. Now, if we have two vertical asymptotes, then they will be asymptotes in two different locations. And again, if they're not repeated like this, then like this one, it goes up to positive infinity. And then when it goes to that asymptote, it flips over. And then it comes back down to negative infinity. And then it flips over again as it goes through that asymptote. Now, it's going to depend exactly what the behavior is. It's going to depend a little bit on your graph. So here, in between, your numerator is always positive. And so in between -1 and 1, your value is going to be negative. And so you're going to be down here. But if you have x minus 4, you're actually going to flip over, because in between -2 and 2, you're going to have a negative in the denominator, but you're also going to have a negative in the numerator, which will make that positive. And so even though they sort of look similar, they have asymptotes in the same places, because the numerator will also be negative and the denominator will be negative, then in this middle section, you're going to get a positive component. So you do have to try to plot values. This one has no x-intercepts. Actually, it has an x-intercept at 4, and we have a y-intercept also up here at 4. And so we can plot those points, and that will give us some information about where our points have to go through. The y-intercept on this previous example was at -1, for instance. And so that tells us horizontal asymptote, I have to be negative here, but this one, if I plug in a very negative or a very positive value, I'm going to get a positive outcome. And so that's going to insist that I'm on the positive side of the horizontal asymptote. And then I flip over to do my intercept. Whereas the reverse will be true in this example. And again, you can see that in some of these cases, you're actually going to cross the axis here. In this case, at x equals 4, that is your x-intercept. Now, in a case like this, again, we have 1x in the numerator. We're going to cross through the intercept. And so we're going to go approaching different infinities rather than in the previous examples, we had an intercept that, and we stayed on one side of the graph. In this case, we're crossing through the in the origin, and then we're flipping over again. So here we're going to negative infinity, we're flipping over to positive infinity, coming back down to negative infinity, and then flipping back up and coming down from positive infinity. So we don't have this sort of section of the graph that looks kind of like a very skinny parabola. Now, if we have two asymptotes, but one of them is repeated, then we can have different behavior. So we can have one of them go to 1 infinity and flip over, and then the other one stay on the same side of the graph. So here we look more like 1 over x squared because the root that has a 0 at 2 is squared. And then at the x plus 2 factor, when x is negative 2, that's going to look more like a traditional 1 over x type of behavior. If we change the x out into the numerator instead of a constant, then again, we're going to go through the origin. And so we're going to go up, we're going to flip over, go through the origin. But then when we come back down, we're going to stay on the positive side of the graph because that x equals x minus 2 squared factor is repeated. And so there's no sign change as you go through that 0. So some other possible variations. So we could have both of the factors squared. For example, we could have one of them squared. Some of them could be negative, so we could have this sort of quasi-parabolic behavior in the middle. So honestly, the only way to really tell the difference between some of these is to plot points, and then you may have to plot a couple of additional points in order to determine, once you have the values, what points you have to pass through. Once you know what points you have to pass through, what side of the horizontal asymptote you're starting on, then that usually will narrow down the possibilities for how the graph is going to have to behave. Whether you're, and then the asymptotes will tell you whether they're repeated or not, whether you have to flip over in sign or whether you don't flip over in sign. It's always a good idea to verify any sketch that you make in your calculator, but you should always try to sketch the graph before you try to put it in your calculator, so that you can try to develop instincts and then verify them in the calculator about how the graphs are going to behave. If you rely too much on technology, if you then are not allowed to use technology on an exam for example, then you're going to be out of luck because you're not going to have any idea about how to proceed other than I need my calculator.